At the heart of a spiral galaxy called the Milky Way, about 4.6 billion years ago, something extraordinary happened. An immense, cold, and dark molecular cloud, made mostly of hydrogen, helium, and grains of cosmic dust, began to collapse in on itself. Its millennial stillness was shattered by a violent event, perhaps the explosion of a nearby supernova, that triggered a shock wave powerful enough to compress the cloud and break its gravitational balance. Thus began the long story of our solar system, not with a sudden creation, but with a slow, swirling process of cosmic transformation. During the gravitational collapse, the cloud, known as the solar nebula, began to rotate faster due to the conservation of angular momentum. Like a figure skater pulling her arms close to her body to spin faster, the cloud accelerated its rotation as it contracted. Gravity and rotation together flattened the cloud into a thin, turbulent disk, with an ever-increasing concentration of matter at its center, a stellar embryo destined to become the Sun. In the central core, pressure and temperature rose vertiginously. At millions of degrees, hydrogen atoms began to fuse into helium, releasing an immense amount of energy. Nuclear fusion had begun, and with it, our Sun was born. Around this newborn star, the disk of gas and dust, called the protoplanetary disk, teemed with activity. It was not a uniform surface, but an intricate structure where physics and chemistry drew the future boundaries of the solar system. The region closest to the Sun, scorching hot, was hostile to the condensation of volatile materials. Here, metals and silicates dominated, heat-resistant elements that formed tiny solid grains. Farther away, where temperatures dropped, water, ammonia, and methane could also solidify, giving rise to icy bodies. Solid materials began to join together through accretion, first tiny particles, then pebbles, then planetesimals, and finally planetary embryos. In this primordial carousel, collisions were frequent, often violent. Some bodies were destroyed, others grew enormously. Thus were born the terrestrial planets, Mercury, Venus, Earth, and Mars. Their inner position, exposed to solar heat, prevented the accumulation of light gases, leaving them compact and rocky. Farther out, beyond the snow line, the boundary where water could freeze, the gas giants formed. Jupiter, the first and most massive, gathered enormous amounts of hydrogen and helium, attracting a retinue of moons as well. Saturn followed, more distant but no less spectacular. Still farther out, Uranus and Neptune captured less gas but retained icy, mysterious cores. But planetary formation was not a linear process. One of today's most accepted hypotheses, the so-called nice model, suggests that, at first, the giant planets were closer together and in different positions than they occupy now. Planetary migration, caused by gravitational interactions with planetesimals and between the planets themselves, would have triggered a chaotic epoch known as the Late Heavy Bombardment. During this period, millions of asteroids and comets were deflected toward the inner regions of the solar system, striking planets and moons, leaving scars still visible on their surfaces. Earth was one of the targets of this cosmic rain, but it emerged with a precious gift: water. According to many theories, it was precisely this bombardment of water-rich comets and asteroids that delivered to our planet the essential liquid for life. And during this same period, in another epochal collision, young Earth was struck by a Mars-sized body, an event so catastrophic that it tore off part of its mantle. The debris flung into orbit gradually came together to form the Moon. Meanwhile, the protoplanetary disk was thinning. Solar winds, powerful streams of particles emitted by the young Sun, swept away the remaining gas, halting the growth of the giant planets and leaving their moons and the asteroids to play the last role in shaping orbital evolution. The most tumultuous phase had ended, but the balance reached was only apparent. Future instabilities, collisions, migrations, and gravitational exchanges would continue to reshape the face of our solar system. And yet, even in this seemingly defined scenario, questions remain. Why have planetary orbits been so stable for billions of years? Are there still massive, unseen bodies lurking at the edges of the system? What role did the largest moons, like Titan and Ganymede, play in the overall gravitational balance? The answers, at least in part, seem to lie in the darkest and most remote zones of our celestial neighborhood, where the Kuiper belt stretches out, and beyond, the hypothetical Oort cloud. In that region past Neptune, where sunlight is as faint as the memory of a star, lie the oldest relics of our system. The Kuiper belt, a vast icy ring populated by billions of objects, represents a kind of cosmic archive. Its bodies, never fully fused or transformed, preserve the primordial chemistry of the solar nebula. Among them stand Pluto, Eris, Makemake, and Haumea, dwarf worlds with eccentric orbits and thin atmospheres that defy rigid classification. Pluto, in particular, revealed during the New Horizons flyby in 2015 a surprisingly young surface, marked by mountains of water ice and possible active geological phenomena. A heresy for what, until recently, was thought to be just a frozen block adrift. Still farther out, where even the Sun's presence is but a gravitational suggestion, lies the hypothesized Oort cloud. A colossal, invisible sphere composed of icy debris and rocky bodies, remnants of the violent expulsion of the first planetesimals by the gas giants. It is thought that many long-period comets originate here, venturing into the inner system on extreme orbits before disappearing again into the deep dark. This region may also hold the key to explaining orbital anomalies observed in trans-Neptunian objects, and fuels the mystery of the infamous Planet 9. A hypothetical, as yet undetected celestial body, perhaps 5 to 10 times more massive than Earth, disturbing the orbits of distant bodies like a gravitational phantom. The search for this hidden planet, as well as the systematic study of Kuiper belt objects, is now at the forefront of scientific attention. With the inauguration of the Vera Rubin Observatory and its LSST, Legacy Survey of Space and Time, a new era will begin. We will be able to observe millions of minor bodies with unprecedented frequency and precision, perhaps confirming the existence of a ninth planet, or rewriting entirely the very concept of the solar frontier. But it is not only distant objects that tell surprising stories. Each moon of the outer giants is a world unto itself. Titan, Saturn's largest moon, possesses a dense atmosphere and lakes of liquid methane, a unique prebiotic laboratory in the solar system. Europa, beneath its icy shell, hides a salty ocean where life could find refuge, far from sunlight but not from heat, supplied by Jupiter's tidal forces. Ganymede and Callisto, both harboring underground liquid water, expand the very notion of habitability, until now tied strictly to distance from the Sun. These moons may be more suitable for life than Mars itself, whose thin atmosphere and tumultuous climatic past today leave only ambiguous traces of possible microbial existence. And while we dream of colonizing the Red Planet, scientific focus is shifting toward robotic missions to these distant worlds. The Europa Clipper probe, arriving in the early 2030s, will explore the subsurface of Jupiter's moon with penetrating radar and sophisticated spectrometers, searching for chemical signatures of life. JUICE, a European mission, will study Ganymede's system, the largest moon in the solar system, even endowed with its own magnetic field. Meanwhile, Earth itself, often forgotten in the frenzy of exploration, continues to evolve in silence. Planetary orbits, though they appear stable, are subject to millennia-long variations called secular perturbations, caused by cross-gravitational influences. Long-term simulations have shown that even a slight instability in Mercury's motion, for example, could, billions of years from now, lead to chaotic alterations of the inner orbits. The end, however, will not come from instability. Rather, it will be the Sun itself that decrees it. In about 5 billion years, our star will enter the final phase of its life cycle. When the hydrogen in its core is exhausted, the Sun will swell into a red giant. Mercury and Venus will be engulfed, and perhaps Earth too will meet the same fate, evaporating beneath an infernal atmosphere. The outer planets, however, will find themselves in a new temporary habitable zone. Titan may melt its frozen seas, and Europa's and Ganymede's subsurface oceans may rise to the surface. After this phase, the Sun will expel its outer layers, forming a planetary nebula, a glowing bubble of gas suspended in the void, leaving behind a compact core, a white dwarf, as large as Earth but 1,000 times denser. Around this stellar remnant may orbit, perhaps in silent harmony, what remains of planets, moons, and asteroids. A system stripped to its bones, but still able to recount the entire story of a stellar cycle. The solar system, born from chaos and the collapse of an ancient cloud, will thus end in a crystallized, mute, perhaps cold form. Yet the traces of its birth, its evolution, its collisions, and its lost worlds will remain suspended in time, like clues left in a celestial archive for whoever, in some distant future, is still able to read them. Perhaps an alien civilization. Perhaps ourselves, returned from a long journey among the stars. If you've made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.